In the previous module, we had introduced longitudinal data. By now, we know that longitudinal data differs from the cross-sectional data in the sense that it allows to include the correlation present in the data to be modeled. So, in this video, we shall be talking about special techniques for exploration of longitudinal data. Now, to explore and visualize longitudinal data, we have to keep in mind two aspects. The first aspect is to model or to have an idea about the mean response and the covariates present in the data. So, this part is quite similar to modeling of non-longitudinal or cross-sectional data, but there are special methods which needs to be allowed and implemented for modeling of the heterogeneity present in the data. Now, to illustrate this, we shall be using the MACS data which we introduced in the last module. So, just to remember of what MACS data is, it's called the multicenter AIDS cohort study data, which contains a total of 2376 observations of CD4 plus cell counts of 369 patients. So, using this data set, we shall be using proper techniques to visualize and to make inference or to explore the nature of the longitudinal data. Now, the goals for visualizing longitudinal data is twofold. The first is to explore the mean response and the covariates. So, what's the relationship between the mean response and the covariates? Secondly, to see about or to infer about the correlation structure and present in the data. Now, while plotting longitudinal data, there are a few things which one needs to keep in mind. The first is, it is always good to show the raw data rather than present some summary statistics of the data. And then to highlight the patterns of scientific interest. The tools should be so chosen that they are able to identify both cross-sectional as well as the longitudinal patterns. And finally, the tools would be able to identify the unusual observations if present in the data. Now, there are basically three techniques again. The first is scatter plots with smoother. Second is called the spaghetti plot. And the third is techniques for exploring correlation structure. So, just a quick recap, it's a total of 2376 observations of CD4 plus cell counts with time since seroconversion for 369 infected men enrolled in the multicenter AIDS cohort study. And here I have provided a link to download the data from the which is available in the internet. Assuming that the data has been downloaded, we can read in the data using the read.table function in R. So here what I have done is I have used the read.table of the data and have stored it in an object called CD4. Now I can plot CD4 with time, and this provides me the simple scatter plot. As there is a large number of observations, this scatter plot is not very informative. The next thing that we can do is we can add a trend line or a smoothing line on the data which shows how CD4 plus cell count behaves with years since seroconversion. So this can be done using the scatter.smooth function in R. For this, no extra packages needed. This is an inbuilt function in R, and we can have the scatter plot as shown below. But why only this? Because scatter.smooth essentially fits what is called a lowest scatter. There are a lot of ways of producing smoothers. One is called the Boxcar smoother. We can have something called the Gaussian kernel smoother. We can have something called the Gaussian lowest smoother. We can have something called the cubic spline smoother. And we have something called super smoothers. So essentially these are different techniques of smoothing the data, and this can be produced using the following set of commands. So here I have given the R code to produce the plots. So I can use the ksmooth command for Boxcar. Again, I can use the ksmooth command specifying kernel equal to normal, and this would produce what is called the Gaussian kernel. Then I can use lowest.smooth, I can use smooth.spline, and I can use the command called SUPSMU, that's the super smoother, to draw each of the smoothers. So what do we conclude from this? We conclude that a scatter plot might not be the best idea for large data sets. For smaller data sets, yes, because in our previous lecture we had seen that for the orthodon data, the scatter plot was good enough. But here, a simple scatter plot does not reveal much. So what do we need? On top of the scatters plot, we need a smoother. The smoother gives an idea about what's the general trend of the response versus the time or any other covariate of interest. And we have the CD. What do we infer from our data here? The CD4 plus counts decrease as time to seroconversion increases. Now, this is at the general or at the population level. What about the individual variations? They are of importance because longitudinal data allows us to study the individual variations. So one way can be, as we did for the orthodon data, is to draw connecting lines for each individuals. However, since we have so many observations for this data set, the problem is that when we draw the plot, it becomes very noisy. We cannot see anything, neither can we infer, so it's all jumbled up. A better way can be to plot randomly a few individuals. So here is the plot. In the previous slide, this is the command to draw the plot. So what we can do is we can specify the number of individuals. Say k is the number of individuals and I have specified it to 5. And then what I have done is I have chosen k random samples from the CD4 data. So that's k individuals from the CD4 data I have chosen and have plotted the entire data. On that entire data, I have superimposed the k individuals trajectory. But again, the problem here is since these are k random individuals, the coverage of the total area might not be good. So for example, we have data out here and data out here and data out here. So the individuals doesn't fall in this region. So what happens is this approach for a large data set again becomes too random. A quick remedy of this is called the SAP plot. Again, here what we do is we rank the study units by some summary measure and highlight those measures who fall at some particular quantiles. Example, we regress Yij on Tij. So now we know Yij is the response of the ith unit at the jth time point and Tij is the associated time point of it. And we get Rij. And we can choose any one-dimensional summary of Rij following Diggle, Liang and Ziegler. I have chosen the median, but this can be any other summary like mean or etc. And then I can plot Rij versus Tij and order units by the summary measure. Finally, can add lines for selected quantiles of the summary measure. Now this is the R code to do this. Now here instead of doing a regression straightforward ordinary least square, I have done a lowest fit and obtained the residuals from the lowest fit. The only reason being that my scatter plot has indicated that the time trend is not a linear one and lowest captures the non-linearity. But for a linear time trend, one can use ordinary least squares also. And here I have calculated the residuals, and then I have used the apply group of function to compute the median, and then I have selected the quantiles of the median. And now what I have done, here I have the scatter plots plotted using this plot command, and superimposed on the scatter plot I have the individuals. So this is the line for the 100th percentile, this is the line for the 50th percentile, this is the line for the 25th percentile. Now this gives me an idea, about the total variation present in the data, how the individuals are varying over time. Now it may so happen that along with time or the unit of repetition, there can be other variables where our importance lies. For example, in this data, we might be also interested in the scientific question that how does age modify the relationship between CD4, depletion of CD4 and time? So we can do what is called a XY plot, and this is present in the library lattice. So we can call the library lattice using the command library lattice, and then XY plot CD4 explained by time, conditional on age. But we see that age there are 369 people, so we have quite a large number of unique ages. Now what we do is we use the function called equal.count, and we use equal.count and within parenthesis age comma 4. Now what does this function do? This function divides the age into 4 overlapping intervals such that each interval has equal number of observations, and then it produces the conditional plot, which is here. And here we can see that the way it is, CD4 plus is depleting with seroconversion, times in seroconversions, or the time is dependent on the age. So for people with higher age, the rate of depletion seems to be faster rather than for people who are at lower age. Might be something to deal with immunity, but that's how. So here what we have done is we have divided the data into 4 overlapping groups of age, plotted the responses. Now to explore the correlation structure, one needs to perform the least square and obtain the residuals. Again, from the residuals, a scatter plot matrix can be generated for group of time or the period in which we are interested, and inferences can be made. Finally, we are left with the correlation structure. So again, here what I have done is CD4.lm is the standard linear model of CD4 versus time, and then I can calculate the residuals of it. And we reshape the data from a long to a wide format and use the pairs command. Now, when we use the pairs command, this is what we get. So we have basically on the diagonals the names of the variable. So these are the residuals at different time points. So this is the residual at 0th year and the residuals at the first year and the second year, and these are the scatter plots. So this scatter plots indicate, so on the y-axis I have residual 1 and on the x-axis I have residual 2. But as we see, fundamentally because we don't know what is the value of each of the scatter plots. And the second point is here there is a repetition because this and this two figures are basically the same. So all the plots in the upper triangular of this plot and the lower triangles of this plot are basically the same, except that the x and the y axis are rotated. For example, here the x axis is residual 1. So here the x-axis is residual for year 1 and the y-axis is residual for year 0. Here the same on the upper triangle, this is year 0 residuals
and this is year 1 residual. So exactly the same plot with the axis being rotated. So how can we improve on this? One thing that can be done is if we keep any one of the scatter plot, and on the others if we can add in the correlation values, that might prove a little bit more insightful. And finally, here we can have histograms of in the diagonal. So what we do is we define two functions called the panel.hist function here, and in second case we define the panel.core function. So the panel.hist functions calculates the histogram. So basically it's a function which takes the input value and calculates or produces the histogram. And the panel.core function, so what it does, it takes the two values x and y and then calculate the correlation. But here I have used only the magnitude of the correlation which is of importance rather than the direction. So I have used an absolute value of it. But if the direction is also important, then this ABS can be removed here because ABS computes the absolute value. And when I incorporate the same Pierce plot, this time specifying that the upper dot panel is panel.core and the diagonal is the panel.hist, it produces the scatter plot at the lower diagonal, the lower triangle matrix. The diagonal produces the histograms, and here at the upper triangle we have the correlation values. Now what happens is this plot instantly gives much more information than the previous plot. So we can see that as time is progressing, the strength of association is decreasing. So closer time we have higher correlation. Over time, as the time is moving, the correlation is reducing. So the correlation gets weaker over time. And it seems that for any two time points, the correlation is dependent on the absolute distance. So this might hint at something called the weak stationarity.
So to conclude our exploratory data analysis for longitudinal data, let us just recap what we have learned. The first thing that we have learned is how to use different kinds of smoothers over a scatter plot to get an idea about the general mean trend of the data. To plot the individual profiles, we have used plots like spaghetti plot and the zap plot, which gives us an idea about the individual level variability present in the data. To include other covariates, we can use the coplot functions of the lattice library like the XY plot to see what is the effect of the covariates on the responses. To model the heterogeneity of the data, we have basically used the correlation plots based on residuals. To do that, we have used pair plots, and in the pair plots we have used the histograms as the diagonals, and for the off diagonal elements we have used the scatter plot and the correlation values.